You are our next speaker, and I don't think we need any further introduction. Would you like to just start your talk?
No.
No? Is this new for you?
I'm nervous. No, I'm not awake yet. I've been complaining all morning that I haven't woken up yet. I'm ready to go back to bed. All right. So, I had a 47-year teaching career at the University of Kansas. And I was known for being very Socratic and very annoying to the students. And I would question them all the time. So at the very end of this, you can expect a spot quiz, all right? Especially from Robert. Robert has all the answers. All right, let's get started here. The flag is in the right place. All right, thank you very much, Marin. It was appreciated. The others doing that. All right, are we ready to go?
Yeah, would you like to use that microphone or you want to hold the microphone?
I'll hold the microphone because I'm going to be nervous and moving around.
Gotcha.
All right.
Let me get this one out of your face in case there's any beauty shots I want to get.
Oh, there is no such thing when it comes to me. No beauty shots. All right, thank you. We're going to talk about the Monarch population development, a state-specific model. I'm going to go into a little bit more detail than a lot of others have gone into. I'm going to try to integrate a lot of things that you've already heard. And the presentation is word heavy, and it's going to require you to take a look at the screen. I'm going to pass over quite a few things because I really don't have enough time to cover everything I'd like to cover here. So what I'm going to be talking about is weather, climate, population stages. I'm going to talk about the collapse, the recovery, east versus west, databases and metrics, the assumptions that we're making and why we are failing, and what's next. That is what we should do next. So you're familiar with this particular image. It's called the scream, and it was in response by this author, or artist Edvard Munch in 1893 to the positions of the clouds and the color of the clouds following a volcanic eruption. He was looking at a change in the weather that was temporary. It was weather. Now we're going to talk about climate change. There's a difference between weather and climate change. Weather is what we're experiencing today, next week, last week, and so on. It's the temporary sort of experience that we have with regard to the climatic conditions. But real climate change is shown here, and it's not shown. So we have, this is a map I put together of the continental United States, which shows the amount of change that has occurred in the growing season, that is from May to September, over the last number of years, that number of decades, from 1975 on. And what you can see here in the red is what's happened to the West. In the West, the temperature has increased remarkably over the decades. About 0.7 of a degree per decade. That's extraordinary. And then you can see that all of the coastal states have higher temperatures than the interior part of the country. So one of the difficulties we have in communicating about climate change is we're not all experiencing the same thing. Those people living in the Midwest are hardly experiencing any change. Those people on the coast are experiencing a lot of change. And the change on the coast is due to the change in oceanic temperatures. Oceanic temperatures have gone way up, and you can see that as a driving force for all of these continental changes. Now, if we reverse this image and just looked at the other months of the year, that is the colder months of the year, it would be the Midwest, which would be showing the most change, and not the coast, because the oceans buffer the winter conditions along the coast. All right, enough about that. Let's talk about my attempt here. So Chip Taylor is trying to enter the School for Western Monarch Studies. It's hard to open that door, believe me. I'm pushing instead of pulling. And anyway, there is a Midville in California, down there in Los Angeles somewhere. So I want to get into a state-specific analysis of population trends. I think we're kind of bogged down in trying to understand how populations function because we haven't really identified the critical systems, the critical processes here. And if you break things down into stages, it's easier to see the processes that are at work. So monarch numbers each season are due to the timing and number entering each stage and the abundance, distribution, quality of milkweeds and nectar, followed by impact of weather, parasites, predators, and pathogens on the numbers entering the next stage. So if you want to have an interest, or you want to have an understanding of what goes into a stage and what comes out of a stage. And so you have to understand the timing and the numbers entering a stage, the conditions that are occurring during a stage, and the conditions that determine the number of butterflies entering the next stage. So here are the stages. I haven't defined the months on this particular slide, but you can imagine the months involved. Right now, we're looking at stage 1, where we're looking at overwintering butterflies in Mexico. Stage 2 will start at the end of February, and that is the return migration into Texas. Stage 3 is the breeding of those returning monarchs, all out in the green area there. And stage 4 is the recolonization of the areas north of 40 North, which is the summer breeding area. And stage 5 is the summer generations, and then stage 6 is the fall migration. So my position is here that if we understand each of these stages accurately, we can make some predictions about what the population is doing. All right, in California and in the West in general, we have a different problem. We don't have one source point. We have something like 4 or 5 source points of monarchs with different climates. So if we look at California, we have butterflies coming from the Northwest region, the West region, which is really the area east of California, and then we're looking at coastal California, interior California, and possibly Arizona, and the other parts of the Southwest. So all of those origins have different climates and different colonization. So in order to understand what's going on in the West, we have to understand how those stages interact with each of those sources. And that's where I've been stuck. I haven't been able to do that. All right, this shows you that some of the problems here. We need to know a lot more about milkweed. And we've seen better slides than this one about milkweed distributions in the West. And we have, in addition to having milkweed distributions, we have to understand what the climate is in all of these areas. Because as Maren showed, once we get above 35 centigrade or 95 Fahrenheit, monarch reproduction is actually quite limited, particularly in areas without vegetation that they can get protection in. All right, let's talk about the differences between the East and West. And I'll go through this very quickly. The East, we have one monarch source and one climate, more or less one climate to deal with. In the West, we have 4 monarch sources and 4 climates. The monarchs overwinter in a small area in the East, and over in the West, you have over 300 sites scattered over approximately 500 miles. You have long migrations in the East and shorter migrations in the West. Strong selection for size, well documented in the East, but you have weaker selection for size in the West, which means that you'll have a lot of small monarchs getting to the overwintering sites in the West that we don't see in the East. Common milkweed in the spring is used in the East, as well as a number of other unique Eastern species. Here, most of your monarchs are coming off of showy milkweed in the interior West, as well as the Northwest. We have a late winter breakup in the East and a midwinter breakup in the West. Females in diapause almost exclusively in the East, and with a lot of females, depending upon the year, breaking up in the West. Then we have winter temperatures that are stable in the East, and winter tables are really quite flexible and variable in the West. So you can see that here. I just dropped this down from a temperature site in El Rosario, Mexico, and you can see that the temperature from the 1st to the 15th of January was pretty much the same every day, and the amplitudes are modest. But you can see here, when I looked at Pismo Beach, I found that there were 4 days where the temperatures reached 70 degrees, and the temperature is quite variable through that period. And so that gives you some understanding of the kind of differences between these overwintering sites. Now, Louis Yang and his colleagues did an interesting study a few years ago, in which they used isotopes and wing size to characterize origin points for these Western populations. And they come up with, I call it Y1, Yang 1, 2, 3, 4, and that kind of redefines these source areas. And we can bring that into focus by talking about these stages that apply to the West. Now, if we have to work with stage-specific information, we have to have a lot of data. And we don't have a lot of data in the West. What we have in the West is data mostly for California, but there's no way I can do a timing and population size estimate off of the iNaturalist data that's available for the West. There's no way I can do anything with the Journey North data in the West. There just isn't enough of it to make sense of what's happening, timing and pace. So my proposed Western monarch stages are overwintering, and in overwintering you have a decline. We have spring dispersal. You can see that would be in May and April. It may be actually earlier than that. We have a first generation, which would be May and June. This really parallels the eastern population. And then you would have summer breeding, which would be from May through September. And then you have the fall migration, which is September, October, and November, depending upon the point of origin. Now, I'm going to talk a little bit about the East, because that's the reference I use to try to understand the West. So, one of the ways to look at data like this is to compare years that are very similar and years that are very different. So here are the 2 years that are the coldest and warmest seasons in the East. And you can see in 1996, we had the largest population ever, 18.19 hectares, and the temperatures in the spring, in March, were well below the long-term average, minus 3.3. That was a deviation. But if we go to 2012, which was the hottest March ever seen in the United States, with 6.8 degrees above normal, the population declined. So we had one of the lowest populations ever seen. I think this is the 4th lowest population ever. So the monarchs declined in 9 out of 11 years with March temperatures of less than 1.9 Fahrenheit, and or greater than 1.4 Fahrenheit, and monarchs increased 4 out of 4 years with March temperatures less than 1.5 below the average. So clearly there's a temperature drive here, and there's a weather drive. So the weather is determining population growth in some ways. We have to figure out how that is determined. And we'll go into some other things. So one of the tests for whether we're dealing with climate change is to look at long-term records. So the record that we have goes from 1994 to 2018 that I've analyzed here. And you can see if we divide that period into 2, we can see that from 2006 to 2018, the temperatures have been increasing primarily in the spring. So we have an increase in March, we have an increase in May as the butterflies are going, the first generation is going north. Very slight increase in June through August, the summer breeding time, and almost no change in the August through September migration, and very little change in the October area when the butterflies are going south through Oklahoma and Texas. So clearly things are in the direction of a climate change thing. We'll have to watch the temperatures that we see in the March in particular. Those temperatures are predicted to go much, much higher than they have been in the past. And so that is a concern because that could lead to lower population numbers. All right, this is hard for you to all read. I'm just going to read a couple of lines here to give you an idea of what I'm looking at. I'm looking at optimal conditions for population growth. In Mexico, we want to have, where they're overwintering from November to April, where we have, where we're wintering and the population is declining. We want to know how those butterflies are surviving, so we want to know what the best conditions are. And those conditions are average temperatures plus water availability, and that will turn out to have low mortality. And you can see, you can go through all of these things, and you can see what I determined to be favorable and unfavorable. Favorable conditions, I haven't listed the unfavorable conditions, that's on the slide that I dropped. But, you know, the opposites of these are also relevant. So factors favoring reproductive success, which we call realized fecundity, low to moderate temperatures, low to moderate wind speeds, and Sufficient rainfall and abundant nectar. Host plant distribution has got to be fairly favorable, and the abundance and quality and sufficient numbers of mates have got to be available as well. The absence or minimal numbers of predators, parasites, and pathogens have got to be a factor here. So fecundity is determined by a lot of interactions with climate as well as other species. So optimal growth outcomes, we get large numbers in optimal timing. Timing is really important. When you come to a species and asking how this population is going to grow, we've got 3 or 4 generations to do it, and the timing has got to be good. If they're really delayed, the number at the end of the year is going to be lower. If the populations are really early, those conditions are favorable for population growth, because you get, aged first reproduction is really important, and the number of generations you can get in is really important as well. So you have optimal conditions and suboptimal conditions, and then you have a mixed result as well. So you can get what I call a straight stick result or a broken stick result. So the conditions can be good in one section, one stage, and bad in another stage. So let's take a look at the years when we had the best population growth. And you can see when you're below, March temperatures are below average, populations tend to grow. May temperatures above average are favorable. Summer temperatures slightly above average are favorable. And we have a single stick for everything that we would talk about here in terms of these stick models for the eastern population. But if we're talking about the west population, we're talking about 4 different origins. We're talking about 4 different sticks for each year. And that makes it complicated. Now, in all the years that I've looked at these data, there's only been 2 years which are mostly a straight stick. In other words, you start out with good conditions, the next step is good conditions, and the third step is good conditions. It just doesn't happen often. Broken sticks are more common than straight sticks. So the West has got a mixed menu of broken sticks and straight sticks year after year after year. So how do you put all that together? I don't know. I haven't been able to do that. All right, population development in 2018 was instructive for the East. In the case of 2018, when we had the last big population in the East, the timing was really extraordinary. We had Texas arrival of first overwintered butterflies. They arrived on time and in very good numbers. The March temperatures in Texas were plus 5.4 Fahrenheit, which would be normally negative, but there was a cap on those high temperatures in Oklahoma. The butterflies were confined to Texas. They did all their egg laying in Texas where the temperature was warmer. The larvae developed really fast. Age to first reproduction was really low. So you had a huge cohort of butterflies coming out of Texas as a result of that, and that limited egg laying in Texas. And we had large numbers of first generation monarchs moving to the north in May and early June. The May temperatures were 6.7 above normal, and that enabled recolonization of huge areas north of 40 North and very early, which was really good. In other words, you got off to a good start in the spring, you got off to a good start in May, and you got off to a good start for your summer generations. And then the summer temperatures were also a little bit higher than normal in the upper Midwest in June and August, with the bottom line that nearly optimal conditions occurred for the entire year. This is a straight stick, and it was impressive. And then I went back through the data and I looked at the last time we had 6 hectares of butterflies in Mexico, and I looked at those conditions. They're almost exactly the same as the conditions in 2018. So there is replication in this stuff if you have enough data, and it's confirming that if you have the right conditions, you will get the right population growth. All right, with the West, don't look at this. Don't even try. I've looked at this for hours and hours and hours. I spent weeks trying to create this, in which I'm trying to put everything together for the West for, from about 1998 onward. And it drove me nuts. I mean, I really can't see anything except really very general patterns out of this. It would be nice to have a narrative for every year, so I can explain the progression through each stage for the West, but I can't do it because we're dealing with 4 origins, 4 climates at least, and we're dealing with the fact that there just isn't any data. So that makes it very difficult. And I'm using means. I'm using means to create all of this. And the problem with means is that they don't account for extraordinary events that happen within each month. So if you have a big winter storm, it isn't necessarily going to show up in the mean. All right, so now that you've not looked at that, let's go on and look at the data sets. So we have a number of data sets in the east that we don't have in the west. We have winter counts in the east. We have first sightings data for March and April. We have first sightings data from May through mid-June. We have eggs per stem data, which is pretty unique. We have numbers tagged. We have fall roosts. We have Cape May, which gives pollen counts. We have NDVI values, which is a measure of greenness, which is a surrogate for the amount of flowers that are out there. We have summer counts from netta and so on and so forth. In the west, what do we have? We have winter counts. And as I said before, we have Journey North information and we have iNaturalist information, but it isn't sufficient in number to really tell us what's going on. So basically, we have one data set in the east. And as I'll get to as we go on here, there's some real questions about how useful that is. And that's going to irritate a few people, but I think we have to be realistic. In the east, I can make predictions. If I know what the conditions are in May, how many butterflies have entered that stage, how many butterflies have colonized, and what the timing was, I can tell you whether the population is going to increase or decrease at the overwintering sites in Mexico, with some provisions, because there are other conditions to deal with. But I can get a pretty good idea whether there's going to be a change. In June, I can predict summer numbers. If I can predict summer numbers, I can predict whether OE is going to increase or decrease, because there's a density-dependent relationship there. In August, I can get a pretty good idea of the size of the migration. And in November, I can make some predictions about the overwintering numbers. I can't do that for the West. So for the West, we really have no predictions that you can reasonably make, except when I go off half-cocked and I make a bet with Robert. And he beat me. He doesn't know anything more than I do. All right, so we've
Aren't
got...
you glad, though, that I beat you?
Well, you
The numbers.
Well, you learn from your failures, right? I mean, that's what... I fail a lot, and after I'm learning a lot, right? That's the way it works. Thank you, Robert. All right. So the reason that we can't make any predictions from the West is we just don't have any data. We've got too many sources here. It's too complicated. No colonization data, no summer counts, no migration data, no data on the reproductive success of these butterflies, and so on and so forth. So now I'm going to bring you to something else, because I'm going to tell you that monarchs are an enzyme, and this is why they're an enzyme. If you look at temperature effects on the butterflies, and you see that you get positive effects under certain conditions, where the population is actually increasing if you have moderate temperatures, and you get negative population growth if you get populations which are experiencing average temperatures that are more than 2 degrees Fahrenheit above average. There's obviously something going on here. The positives and negatives vary. And so the impacts of temperature extremes vary with the seasons and the location. High temperatures enhance dispersal in the spring and slow the migration in the fall. So you have to be careful how you use the temperature data, because you have to understand how the butterflies respond to the temperature data. Which brings me to this, which I proposed, I think, last time I was here, or shortly thereafter, that monarchs are an enzyme. Which means, in effect, there is a developmental zero at the lower end, developmental zero at the upper end, and there is an optimal peak for development. It's also an optimal peak for size and mass, lipid stores, flight, oviposition temperatures, light intensity, wind speed. So you get all these responses of the butterflies to the physical conditions that have optima. And it depends upon what the behavior is at a particular time. It would probably surprise you to know that humans have behaved like an enzyme as well. We have our lower optimum, we have our upper lower developmental zero, we have our upper developmental zero under extreme conditions. But all of this interacts with resources, so we have to understand the resources as well as all of these optima, all right? So And you have to understand how weather interacts with all of this. Well, with that, with trying to understand how temperature impacts butterflies in various ways, I wanted to see whether I could make something out of what happened in 2018 here in the West. And we heard a little bit about that from others earlier. And I've got 3 minutes left, and let's see if I can get it. So in the summer of 2017, and where are my glasses? Anyway, we had the second highest temperature in record. October to December, we had the second highest temperature in the record as well. Both of those are strong negatives. January, February, we had the third highest in the record, and those are negative. And then in March, April, we had positive, but they apparently didn't really, they broke the stick, but they probably were not that positive. In May, September, again, we had the lowest record for precipitation, and we had another negative. And then May, September, again, where we had in the West, we had the highest in the record, and strong negative, and another week positive. Anyway, the scenario for 2017 through February of 2018 with a low return followed by high mortality of overwintering monarchs, partly due to those storms we heard about, and due to the consistently high temperatures, low and late dispersal of surviving monarchs in March and April, followed by high temperatures in both the Northwest and West, and the drought conditions kind of doomed the population in terms of real positive growth. So how can we explain the increase from 2020 to 2021? Well, we had Thanksgiving counts of 1849 butterflies, and that's just not enough butterflies to produce 247,000 butterflies in the next year. And females tend to be about 45% of the population. So even in the best conditions, we would have 832 females. But given the distance and time involved from reproduction, we have counts in November that, let's see, the females had to be much lower, probably 500 or less. So there had to be more females, but how many and where were they? Well, the short answer is that we had to have at least 10,000 females out there to produce a population of at least 300,000 butterflies. So I have a long diatribe on all of this that's going to appear on our blog. It's over 6,000 words. Don't read this, but this is just the summary of it, and explaining probably what happened in that interval from 2017 to 2020, fall of 2021. Now, what happened in part had to do with this particular chart right here. Look at San Luis Obispo County, California average temperatures. They were the highest on the record going to 1895 in September and October. And that was a killer. It meant that this is the short-lived version of this recovery. The hottest September ever in the records from 1895. Most monarchs did not reach the coastal areas. Monarchs spent winter as singles and in small clusters in the coastal foothills. Breeding continued through the winter along the coast. Offspring from winter breeding and monarchs in the foothills reproduced inland in March. Combined female cohort numbered in the thousands. Large first generation colonized intermountain states, and May-June conditions resulted in a large migratory population of at least 300,000 butterflies for the fall. Now I'm going to take a shot at a couple of assumptions here. And one of the assumptions is that these fall counts accurately represent what the population is. Butterflies seem to be on the move all the time, so when is the optimal time? Or does it change from year to year in terms of making those counts? We don't know. We're making assumptions that it's a really useful metric, and it may be a metric that's really off from time to time, as it seemed to be in that year when we have extremely low numbers. The mean temperatures and precipitation accurately reflect conditions, probably not. That's probably a false assumption. The changes that I've identified truly represent the processes. They may or may not. Positive and negative impacts of physical factors as derived from the east apply to the west. Probably do. A butterfly is a butterfly is a butterfly. Contributions to overwintering numbers are relatively similar each year from the west and from all of these overwintering sites, or all those reproduction sites, and that's probably not true. So we have a lot of data gaps. I think you can appreciate that. I've run over my time, but we don't have data for the West. And there is an opportunity for all of you in the West to figure out how to get the data. We need a lot of data if we're going to figure out what's going on here in the West. I can't do it and I've spent weeks trying to figure this out. And here are some environmental conclusions. I'm not going to run through all of this, but the mean temperatures along the California coastline have increased an average of 2 degrees Fahrenheit since 2020. Things are really changing, and we have to monitor those changes. We have to measure those changes. We have to determine what the impact of those changes are going to be on the butterflies. As you probably know from what I told you, 2020, these butterflies are moving further north. Overwintering sites are disappearing in the southern 5 counties of California. Let's see. What else do I want to tell you? I want to go on here. All right, I've overrun my time, so I'll let you imagine the rest. But I want to leave you with a couple of things. It's true, butterflies aren't free. If we have value monarchs and pollinators, we will have to invest in their conservation. As part of this process, we need to reduce greenhouse gas emissions. There's no funny business about that. So basically it comes down to 2 things. We have to maintain habitat, and we have to advocate for change in our policies that deal with the things that are changing the planet. And from here, I get these questions. Robert, thank you very much. I didn't think you had your hand raised. Professor Taylor, can I be excused? My brain is full. Yes, Robert, I quite understand. Are you ready for the quiz?
Would you like to color with me?
All right. Well, Toto and I would like to thank you for listening, and thanks to all the citizen scientists, and others who have. For getting us all together. We've got a lot of great teammates that have made this all happen.
Yes.
They deserve the recognition as well. Right?
Good morning, everyone. I'm Terry Smith, Pollinator Posse in Northern California. And I love your talk about data. I'm a data geek. We started the morning with recognizing our youth, and I was lucky enough to work with Elaine. We consider her a part of the posse. So that was really wonderful as a teacher to work with someone who has really achieved what she set out to do. But as Mia Monroe reminded me last night at dinner, when she gave me the whole history of the Xerces count, there have been many people who have gone before any of us in this room who have done huge amounts of work. And Chip is the max of that. I don't have the right words. I was lucky enough at the last conference to sit and chat with Chip. And he shared with me his experiences sending monarchs up to the space station. And I apologize, I don't even remember what the point was, but he sent monarchs to the space station. And we stand on the shoulders of giants. We are working today because of the work people like Chip did in the past. So we have a couple of things for you. One, because you're our foundation, we have one of the lovely rocks that Ida has painted to add to your, I'm sure, extensive collection.
It looks like a curling rock, right? Except it's not big enough. Still,
So, and as I'm sure most of you know, Chip is quote unquote retiring, and his version of retirement, which I totally understand, is that he's retiring to finish books and work on projects, right? So actually, my personal perspective, and I want to share this with you, is that it's not retirement, it's metamorphosis. But what he has done to make sure his work continues is he set up an endowment to continue his work with Monarch Watch, which he founded, and his work in Kansas. So we want to support that effort as a group. And so we do have a donation to your endowment fund.
Thank you.
From any of the people in this room and from Western Monarch Advocates. And we really appreciate everything you've done, and we all stand on your shoulders.
Well, thank you very much. Thank you very much. I really appreciate it. You know, I debated and Robert and I went back and forth, and I said I wasn't coming until I was. And I had a bad experience with an airplane, and I said, I'm not going to travel anymore. But this is, you know, seeing Robert again, I just had to come out here again. I mean, he's such a gentle soul, and he's so easy to harass. Anyway, we love you, Robert, and thank you for bringing us all together, and thank you for this contribution to our endowment fund. We really appreciate it. Thank you very, very much.
Everybody.